Hi, this is Shelley Physics, episode on contact forces, including normal force and friction. So contact force is when two solid objects come into contact. It's atom against atom. What happens? There's both a horizontal force, which we call friction, and a perpendicular force called normal force. So in this diagram, it's the ground that's holding up the block. There's an upward normal force in this direction, pushing up from the ground. That's because the weight of the block pulls down. So the weight of the block's pulling it into the surface, and the surface is pushing back with an equal amount in this particular instance. Now that's not to differentiate there. That's not the Newton's third law reaction force. The reaction to gravity pulling a block down is the block pulling the earth back up. So but in the reaction to the table pushing up on the block is the block pushing down on the table, which we're going to see a little bit of that reaction force later on in this episode. So we get the normal force. This is that perpendicular contact force. And then if we give this block a little push, there's a push here, then what's going to happen? There's going to be some friction that is working against that pushing force. So there's going to be some friction here, and that is the contact force that is parallel to the surface, okay, the horizontal contact force. So those two are the key elements here, and the relationship between those is that friction is mu times normal force. And this was introduced a little bit earlier. So what happens here is if we plot a graph of normal force versus friction. And let's say we're just giving this a little push, and we're going to pile up more and more masses. So if we change the mass, change the weight of this block, that'll change the normal force. And you'll find that with no contact, with nothing pushing the block against the surface, there is zero friction. So there's a point down there. And as we add more and more weight, the increase in normal force also increases the friction. And depending on that amount, depending on actually the surfaces, how much grip there is between that block and the tabletop, that's going to affect how steep this line is. Okay, but generally what happens is if you add weight to a block, the friction will increase. That's why you take your dresser drawers out of the dresser if you want to move it across the room, because taking that weight away decreases the frictional force, and it's easier to move that dresser. But the slope of this line, if you think about this line that you get, it's, line function is y equals mx plus b. On the y-axis, we've got friction. On the x-axis, we've got normal force. And where does it intersect the y-axis here? Down in 0, so the b is 0. And that leaves us this little m. Well, m is the letter for mass, so what else could this slope be? We can't use m, so we're going to use the Greek letter m, mu. And that's where this formula comes from. And different surfaces, let's say, what if we put this block on ice? Not like kill it, okay? We're not like gangsters here, okay? But I should say gangsters, because that would be more of the, never mind. If we put it on ice, then the friction increase won't be as much as if it's on a tabletop. So the slope will be less, the mu value will be less. Or what if we stick some glue and some glue between the block and the table, and it starts to harden a little bit, then we might get a really sticky, grippy surface, and we might have a really steep slope, a really high mu value. So that's where it's all coming from. It's a relationship between normal force and friction. You'll notice this is a force in units of newtons, and over here is a force in units of newtons. So that means that coefficient in front is just a coefficient. It is unitless. Okay, so this mu is called the coefficient of friction. It's the degree of grip. That's what I like to call it. How grippy are the two surfaces together? If you splash water on the tabletop, that changes the mu. Now there's not just one mu value, all right? There are actually two, because there's two kinds of friction. You see, to get that big dresser in a room moving, you know how it's harder to get it started than it is to keep it moving once you have it started? There's that, it's settling. It kind of settles into that surface. You see, if you can zoom in on these two surfaces that are in contact, you'll probably notice that at their atomic level, they're two very rough surfaces, and they're very uneven. Those atomic surfaces are very uneven. So you can imagine when this block pressed against the table these little crags are gonna interact, and they're gonna grip to one another. It's gonna make it difficult to move side to side. But at the same time, the tabletop is gonna put an upward force on that block. So there's the normal force, and that side to side resisting force is friction. So if we try to push the block to the left, there's going to be friction to the right resisting it. All right, this the surface will push back as the blue, let's say this little piece settles into that little spot. That blue is going to push the red forward, the red's going to push the blue back. So there's an equal and opposite reaction force going on there also. All right, so that's that contact forces at the atomic level. Now, if get back to the two types of mu, the two types of coefficients of friction, comes from static and kinetic friction. So when that block is settled, the blue on top is settled down into the red on the bottom. It's like you got to lift those big old bumps up the little mountain here. Okay, so that little surface there is going to interact with this one. They're going to push on each other. It makes it more difficult to move. But once you got them sliding, then that red surface, or that blue surface up there, let's see if I can get this to move. That's not going to move separate. But you can imagine that blue surface moving or gliding. It's almost like it's skipping over waves as it moves forward. So the kinetic friction is going to be less. So there's an associated mu static. This is the coefficient of static friction. And mu k, which is the coefficient of kinetic friction. Now the static is going to be greater than the kinetic. Just remember that, because it's harder to get something started its motion than it is to keep it moving. Another example of this, cutting a bagel. Oh, if you ever learn to cut a bagel, you know that you never cut towards your hand, because when that knife gets stuck in the bagel and you push it a little bit harder, you're trying to overcome the static friction, and zoop! Once that static friction is overcome, the knife goes flying through that bagel, and you're in danger of cutting yourself. So if we compare like a pushing force in that scenario, the force of push, like the pushing force, to friction, right? What happens in the beginning is if you push on a dresser just a little bit, you might notice that it doesn't move. You push a little harder, it still doesn't move. But once you push just hard enough, it's a little easier to move. So what happens as you push harder and harder, friction increases and increases and increases until you get to this certain point where it drops a little bit, and then it seems to be about constant. And I did waver that a little bit because surfaces are uneven. So you get a little bit more here and a little bit less there. But overall, there's sort of an average value. If you do the 2 ways to find mu video in my series, you're going to see this in the lab data. You're going to see this increasing frictional force as we increase the push, and then it'll drop down a little bit. We'll be looking at the maximum there. This corresponds to mu s times the normal force of the block. And this little section down here corresponds to mu k times the normal force. You see, this is the kinetic friction amount, and this value is the static friction amount. Now, up here, do you see how the static friction responds to the push? Down here, the static friction is small, then it increases and increases and increases. So this is actually a maximum static friction, a maximum static frictional amount, how it relates to normal force there. So as you can see, as you push the dresser harder and harder and harder, and it doesn't move. Eventually, you get to that point where it just starts to move under your pressure. So that means static friction is actually less than or equal to the coefficient of static friction times normal force. And once you get that sucker moving, the kinetic friction is constant. It's equal to mu k times normal force. So you're going to see friction appear in both these forms. Some questions might ask something about how much force does it take to start the motion of this block or this object. If it's saying how much force does it take to start the motion, that means there was no motion to begin with. We're talking about static friction holding that object at rest. And another question might ask, how much force does it take to continue pushing that object at a constant speed? Or as the object's sliding along the ground with this force applied, what is the acceleration of the object? That implies that there's an object sliding over a surface. If the scenario where you can hear that sound of friction, that's a kinetic friction. If it's a friction that holds things at rest and you don't hear anything moving or sliding, that's a static friction. Rolling friction, like from wheels, that's also a static friction unless you hear the wheels squeal and slide and screech. You always want the wheels, like on a car, to come down and grip the road. You don't want it sliding across the road. All right, so that's just a little bit of insight on the static and kinetic friction, how they relate there. So let's get into some problems here. Here we have a block being pushed at an angle along a rough ground. And we're asked to determine the force if V is constant, and that pushing force if the acceleration is 2 meters per second squared. So here we are sliding this block. So we're going to need to know a mu k also, and I'm going to supply that. Say it's kind of a slick surface, and we'll just start with a 0.2. So this is a coefficient. There's no units. This is something that's measurable in a lab situation. Again, you can take this block and compare different weights to the kinetic friction, and you'll get a particular line. So once you measure that rise over run, or calculate that rise over run as a slope, that's the mu value. So these are always experimentally determined. All right, so there's a scenario. And I'm going to refer to the problem-solving process. First, we're going to draw a force diagram, label the force vector arrows with all the knowns, unknowns, and such. Our orientation is just going to be straight up and down here. There's no slope. So we're going to move on to 3. If there's any angled forces, which we do have, we're going to resolve those into components. And we're going to be applying Newton's second law in both the x and the y direction to get a system of equations that we can solve. All right. So move back. Force diagram, first step. Here's our block, 20 kilograms. It has a weight to it, mg. That's 20 times g is 9.8 here on Earth. We're assuming Earth, not Mars or the Moon. So that value is 196 newtons. Next, there's this pushing force, and it's angled. I'm going to move it down here. It's angled down this way. In a force diagram, you always put the forces coming out of the object. So there's the force, a pushing force, and I'm going to label this angle 30 degrees there. Okay, we've got a little bisecting line situation here. If you've got horizontal and a bisector like that, then this angle, which is 30 degrees, equals this angle, which is also 30 degrees. Okay, so congruent angles in these bisecting lines. Let's back that up. All right, are there any other forces here? We've got the pushing force, the weight. Oh, there's friction, right? So if this block is being pushed down into the right, so down to the right, there's your perspective there. The block isn't going to go into the floor. We've got a floor that can support its weight. So there is going to be a friction, though, to the left. So there's going to be a right-hand motion to this block. That means the friction is going to be pushing to the left. So we're going to label the friction. It's supposed to be a left-hand arrow there, going directly to the left. And wow, we've got forces down, left, and right. What about up? We've got normal force going up. Now, as I look at this, I'm going to reason here that the weight and there's a downward component of this pushing force. We're pushing this block partly into the ground. So there's the weight plus a little bit of pushing force. That means the ground is going to have to apply a normal force greater than the weight to equal the sum of the downward component of F, which is the thing that we're looking for here, and the weight. So the sum of the weight and the downward component of F. So that, look out for that. If there's ever a force pushing down, then the normal force is not equal to the weight, which is one of the reasons I brought up this problem here. So we're done with step one, I think. We've got this pushing force, normal force, friction, and weight. Next step, is there an orientation we should respond to? No. I think left and right is right hand direction is the direction it's going to accelerate in, so we want to keep that as our X direction. Now let's resolve the forces and draw a force diagram. Okay, here we go. So new force diagram. I'm going to draw that up here. We've got 196, friction to the left, a big normal force up. Here's our two contact forces, normal force and friction. It happened because that block is in contact with the ground. And friction, or this pushing force over here, is going to have a component to the right and a component down. Don't forget that down component. I've seen a lot of students have trouble because of that, just forgetting that downward component. All right, so the component to the right is adjacent to the 30-degree angle. So that is going to be F cosine 30 degrees. F is the hypotenuse. The adjacent side gives us the cosine of 30. And that makes this vertical side, the piece that we're kind of thinking about here as a right triangle. There's a horizontal and the vertical piece. So this vertical piece is this little guy over here. And that's going to be the sine component, F sine 30. All right, we've got all the forces accounted for. They're all in the X and the Y direction. So we're going to apply Newton's second law. I always like to start with the Y direction, because sometimes, you know, that has the weight involved. Sometimes that's the only direction we're going to need. I think we're going to need both of them in this case, because we do need to incorporate friction. So that equals m, acceleration in the Y. And we're also going to remember not to forget the X direction. Okay, so we'll treat these a little separate here. So in the Y direction, we got normal force going up. We're going to add a negative 196. Weight is working against that normal force. And also we've got this F sine 30 working downward. I'm using up as the positive direction, so any downward forces are negative. That is the sum of all the forces in the Y direction. You don't have to put parentheses around it. I'm just putting it there for clarity, that all these are the sum of the forces in the Y direction. Now this is a 20 kilogram block, so there's the mass. And is A in the Y direction what we're looking for? No, we actually already know it. If there's a downward push and the floor is completely supporting it, then the acceleration in the Y direction is 0. You don't have to worry about that. So there we go. And here we have normal force minus F sine 30. And I'm gonna add 196 to both sides. So it just equals 196. It's just so we don't have an equal 0 on the other side. Just makes this a little smaller. So we can't solve for what F is just yet. We don't know what it is. So when you get stuck, don't stop. Let's go to the other side. In the X direction, we got an F cos 30 going to the right, and a force of friction going to the left. And that equals 20 times A. Now I'm going to leave A kind of open here because we have two different situations we're going to be looking at here in a second. So we're going to apply that when we need to. All right. So here we go. We've got F cosine 30 minus force of friction equals 20A. This thing will be accelerating to the right or not. Okay. If V is constant, then that means the acceleration in the X direction is 0. And if A is 2 meters per second, we're assuming to the right here, that means that is AX right there also. So we're going to look at these two different scenarios and just get a slightly different response out of them. All right, but I've got a lot of things going on here. I've got a normal force, an unknown F, There's the F again, so there's a connection between these two equations. We got an A value, we're going to plug those in. So we know A, we can check that one off there. And we got this friction, but friction and normal force are related. So in my problem solving process here, I put a little reminder, substitute expressions for forces where appropriate. And it looks like it's a good idea now because friction is mu times normal force. Okay, it's there to help you. Please use that list. Check it off if you get stuck. So we're going to substitute friction here, and this is a kinetic friction. So I can substitute mu k times normal force. All right, and now if we look at this, we got normal force, F, and do we know everything else? We know the mu k, the coefficient of kinetic friction, is 0.2, and we're going to be able to plug in an A for each situation. So we're actually ready to go. We have two equations with two unknowns. All right, so if we're actually looking for F, what I'm going to do is solve this one for Fn and plug that result in over here. That'll eliminate normal force from this equation set. So Fn would equal 196 plus F sine 30. And hopefully that makes sense. The normal force up equals the weight plus the downward component of the pushing force down. All right, and we're going to plug those in right over here. Let's give us some more room. So I'm going to just rewrite this equation right down here. F cos 30 minus, I'm going to go ahead and plug in mu k, 0.2 times the normal force is 196 plus F sine 30 equals 20A. I'm gonna simplify this as much as I can before I plug in an A, just so I can get both of my answers all at once here. Let's distribute this 0.2. I'm gonna need my calculator for this. All right, so we got an F cos 30 minus, we got 0.2 times 196 is 39.2. And then negative 0.2 times F sine 30. F sine 30 is a half, but we'll still get a negative here, so 0.2 times sine 30 is 0.1, half of 0.2. I don't know where I was going with that one. So we're going to have a 0.1 F out here. Okay, so 0.2 times a half times F gives me a 0.1 F, and all that equals 20A. And I can combine like terms. We got an F cos 30 and a 0.1, so we're going to take cos 30, which is 0.866, minus 0.1 F. I'll go ahead and write that out. 0.866 F minus 0.1 F, and add 39.2 to the other side. I'll go ahead and do that. Equals 20A plus 39.2. Okay, and we got a 0.766 F equals 20A plus 39.2. Excellent. So now we can put in our two conditions. For A, constant velocity means acceleration is 0. So we're going to have 0.766 F equals 0 plus 39.2. And divide both sides by 0.766. And we get a force there, 39.2. Look how easy that is in the end. 39.2 divided by 0.766. Easy meaning it's reduced down to something pretty simple. Just use it, system equations together. We got a 51.2 newtons. Or if you use sig figs, probably about 51 newtons. And B, if A is 2 meters per second squared. All right, then we're just going to have a 0.766F. Give us a little more room. Equals 20 times 2 meters per second squared. It's a 39.2. So that'd be 40 plus 39.2 is 79.2 divided by 0.766. And I got 103. So F is now 103 newtons. All right, there they are. Solve for both of them. All right. Just a quick recap. I'm not doing anything new. I'm taking a force diagram. I'm resolving it to its components. I'm applying Newton's second law. The slightly new thing here is we're substituting mu times normal force for friction. Just look out for that. If you ever have friction in there and a mu is given, or you're looking, the target might be the mu value, like we're going to see in this next problem, include that there. You throw it in there, mu times normal force. And the rest is plug and chug algebra. All right. Next situation. This might be helpful for the friction lab. If you did 2 ways to find mu, this is the second way. If you take a block and increase the angle until it just starts to slide, that's going to help you find the static coefficient of friction. Now in this kind of scenario, I'm asking you kind of the opposite. What would the angle be to give us the mu s? I'm sorry, what would the angle be to start the block's motion given a coefficient of static friction of 0.42? We got a 20 kilogram block here. All right, so this will be a little reminiscent of a block on a ramp problem. Draw a force diagram. There's its weight going straight down, which is again going to be 196 newtons. Okay, that's mg. Just calculate that. Normal force is going perpendicular to that slope. You got an angled force, so let me put that in. Theta is the unknown. And to keep this block at rest, the static friction has to be going parallel to the surface. There's our contact force is a normal force that's perpendicular, and friction will be the parallel force. That's also theta. All right. Now the tendency of this block is to move in this direction. So that's like a positive direction there. If you look at the system, everything's pointing to down the slope being our x direction and perpendicular to the slope. So parallel slope being our horizontal plane and perpendicular to the slope being the vertical, the y direction plane. All right, so that would be a better perspective here. So thinking about the problem solving process, we're going to determine the most appropriate orientation and redraw, and then take any angled forces and put them in their component form. Okay. All right, so I think we've labeled everything and given values to everything we know. Now what I'd like to do is just kind of rotate your head a little bit, go it that way and look at it. And now your normal force is straight up and friction is in the x direction, okay, in your new view. And this block would have a tendency to go in the opposite direction of friction. So whatever direction things accelerate in or have a tendency to accelerate in, those are the directions that you want your x direction to be in. So just rotate your view so that normal force is straight up. That friction is now, so if normal force is straight up, friction is going to be to the right along the base there. And if this is now our y direction, that means the weight is kind of off in this direction, 196 newtons. And this angle is going to be the same as that angle. You see that theta and this theta, they're congruent angles opposite there. So this is also the angle of the incline. If you need more help with that, look back at the original Newton's second law applications block on a ramp or block on an incline video. Okay, I'll go over that a little bit more in that video. All right, so we've got this so far, and our next step is to turn that into forces that are all in the x and y direction. So let's redraw normal force again. That vector, we've got friction vector going to the right. And let's break up this 196 newtons into its down and left components. Okay. Now I'm drawing the left component about equal to the friction because we're trying to remember that static friction from this video is less than or equal to mu s times normal force. So when I start inclining this ramp this way, the block is going to stay stuck. I'm going to incline a little bit more. It's going to still be stuck because static friction is less than or equal to this maximum amount, mu s times normal force. But when we hit this point where when static friction is equal to mu s times normal force, it'll begin to slide. Or I should really say it'll begin to slide just after that point, just after that angle. Okay, it'll begin to slide. Wow, that does not look very clear at all. My apologies, audience. Okay, so moving on. This downward component of 196 is the cosine component. It's adjacent to that angle. So we're going to have 196 cosine of theta, our unknown theta, and that makes this component 196 sine theta. There's another familiar thing, the component down the rope, down parallel and down the ramp is the sine component, and the component into the ramp is the cosine component. So now we can sum the forces in the y direction and the x direction. All right, y direction, we've got a normal force minus 196 cos theta equals mass time. Oh, wait a second. Is it accelerating up or down? No. That acceleration in our new y direction is 0. Okay, up or down in the ramp, it's not happening. So left and right, it may happen, but up and down, it's not. So we know this is 0. Acceleration is 0. And here we see that the normal force is equal to 196 cosine theta. All right. Looking ahead, you're going to need that for friction. All right, and here comes friction. To the left, we've got 196 sine theta. To the right, in the opposite direction, we've got friction. And then we've got a 20 kilogram mass. But wait, so we need to find the angle to just start the block's motion. So it's actually not moving yet, but it's reached a point where static friction is equal to mu times normal force. So we still have a 0 acceleration in the x direction. If we go any higher than this angle, it's going to start sliding and accelerating. It's going to start engaging its kinetic friction instead of static. So it'll start moving. So acceleration is still 0 here, but we're at a point where we can substitute mu s times normal force so that the acceleration is still 0, but it's at its maximum frictional force, okay? Maximum static friction there. All right. So, okay, what do we got here? We've got everything involved. We've got a theta normal force, be able to plug it in over here. We've got the mu s is 0.42, so I think we're ready to solve this. If we take this and plug it in over here, let's see what happens. We're going to end up with a 196 sine theta minus 0.42. You know what? I'm just going to leave it as mu for now. Mu s times 196 cosine theta equals 0. Okay. If we're going to solve for theta, we got to combine these somehow. Let's try adding mu s times 196 cosine theta to the other side. Let's just see it slightly differently. We add it to both sides, cancels on the left and gets added to the right. And look what happens here. We can divide both sides by 196, and the weight completely cancels out. Isn't that wonderful? No more weight, and we've got sine theta equals mu s times cosine theta. And if you know your trig identities, what can you do here? We can divide both sides by cos theta. And what is that? Mu s is equal to sine theta over cos theta. And if you know your trig functions, sine is opposite over hypotenuse, and we're dividing it by cosine theta, which is adjacent divided by hypotenuse. And if you look at that big division line there, the hypotenuses cancel out and we end up with opposite over adjacent, which is tangent theta. Okay, so this is the same as tan theta is mu s. So what? All these unit values cancel out, and we're left with a mu s equals tan theta. A coefficient equals a number. Hey, that's possible. There's no more, right here, the newtons canceled out with the newtons, all right? No more newtons left. And we get the little fact here, that angle would be the inverse tangent of the coefficient of static friction. Woot! Let's just plug it in. What's inverse tangent of 0.42? There we go. What angle will this be at? (22.8 degrees). There it is. At 22.8 degrees, any higher than that, 22.9, this block is going to start to slide. Now, all surfaces are inherently not perfect. So sometimes in some parts of the block, it may be a little bit more angle needed, and other parts of the block will be a little bit less angle needed, but somewhere around 22.8, it's going to start to slide. All right, our final example. Whoa, this is a pulley system. And I wanted to get a little bit of action-reaction force that's going to be happening here. So there's going to be several, or just a couple of different normal forces to consider. Okay, in this scenario, there's actually a couple of different tensions involved. They are all internal, and there is a way to look at this in the system method as well, using that system view. But because there's several things involved here, I think I'm going to piece this apart for you, and just to make sure we don't get too many things loaded on top, because it can look pretty funky in that system view, and it might not make a whole lot of sense if I do it that way. So I'm going to call this mass number 1, 2, and 3. Okay, mass 1, 2, and 3. Here they are. All right. Ooh, so there's a few things involved here, and this may make it look complex or hard. It's not really complex or hard. It's just kind of bloated. Okay, just more stuff, and that's all. We're still going to do the same thing. We're going to apply Newton's second law after doing a force diagram. Nice thing about this one is there's no angles. So let's start with force diagram number 1. So this is block 1. There is, we're looking for the acceleration of the system. So here's block 1. It's got the weight going down, which is going to be 20 times 9.8. There's our favorite number, 196 newtons, that we keep seeing in these problems. Here it is. And there's a tension upward. Now, there's a tension here, and there's going to be a different tension here. So I'm going to call this one T1. Let's call that T1. And we'll call this one over here T2. It might look a little funky here, but T2 is also to the right up here. The pulley changes the normal direction there. But if you look at that, like in terms of the pulley, this tension is going into the pulley, and this one's also going into the pulleys from opposite directions of the pulley. So these are in opposite directions. But getting back to this one, T1, how should we draw this? Should we draw it short? Should we draw it the same length? Should we draw it larger? Well, to figure that out, we need to consider what direction, if any, that this block is going to accelerate in. Now, if we assume the system is going to be moving and accelerating, let's say this thing should be going down. Are we going to assume that the acceleration is down? So let's call down positive. And if it is accelerating downward, all right, if it's accelerating downward, then that means the downward force on block 1 has to be greater than the upward force. Down has to be greater than the up, and the up is that tension 1. So I'm going to draw tension 1 shorter. That's important to realize. If the system were at rest, then they would be equal. The weight would be equal to the upward tension force. But since it's accelerating downward, or at least I'm assuming that, I'm going to say down is positive and the acceleration is down. So what we have to do is keep that consistent with these other two blocks. So let's go to block 2 now. All the forces are done with block 1. Here's block 2. It has a weight of 10 times 9.8. Now to your eye, 10 kilogram block may look bigger than the 20 kilogram block, but it's made of a different material, different density. All right, anyway. So 10 times 9.8 is 98 newtons. All right, now, what's going on here? We've got an upward force from, let's call this a normal force. I'll just put this up this way. Call it Fn. And, there's a block sitting on top of it. What is this 5 kilogram block going to do to the 10 kilogram block? It's going to put a force down. What kind of force is it? It's a force from a solid surface. And what will the 10 kilogram block be doing to the 5? Do you see how that 10 is acting kind of like a table surface to the 5? So that 10 kilogram block is pushing up on the 5 kilogram block with normal force. And the 5 is pushing back down on the 10 kilogram block also with normal force. But this normal force down here is different than this force up here. That 5 kilograms pushing down on that one, this is the table pushing up on block number 2. So there's also going to be another normal force here, and we can't really call them the same thing. This one's from the table, and this one's from the block. So I'm going to write normal force from the table, and this is the normal force with the blocks. And that should go along with these guys up here. We'll call this the table block mu, T, and this one the block mu, B. Well, it looks like I use a capital T. So I use a capital T and a capital B. There, we got those labeled. So these are going to be sliding against each other. We're going to have a kinetic friction of that slide. Get back to the kinetic friction. All right, so there's a downward weight. There's a downward normal force from the up the block on top, and there's an upward normal force from the table pushing on block 2. And of course, I can't forget these tensions here. There's tension 1 to the left, and how about tension 2? Is that equal, smaller, or bigger than tension 1? Well, if block 1 is falling down, then block 2 is going to be moving to the left. So we're going to say left is positive to keep that, and that's going to be the direction of our acceleration. Keep that consistent between these. And if it's being accelerated to the left, that means the left force has to be greater than the right force. So T1 should be greater than T2. I'm going to make that a little bit shorter than T1. All right, I'm going to clean that up in a moment. We'll come back to that. And block 3. This one should be a bit simpler. There's a weight from block 3, 5 kilograms times 9.8 meters per second squared is 49 newtons. And there's a upward normal force from block 2. And you see how, block 3 is pushing down on block 2? Here's that action-reaction force. If the 5 kg block pushes down on the 10, then the 10 pushes up on the 5. And that's going to be the normal force, Fn, from the blocks, not the table, because they're not in contact. All right. And we've also got a tension 2 pulling to this direction. Tension 2 connects these two blocks. All right, am I done? Whoops, I forgot something really important here. friction, right? If you're going back here, well, it's shoulder, you forgot about friction. You're right, you're right. So I did want to leave that to this point. Well, once we had 2 and 3 up here, because just like there's a action-reaction pair of normal forces, there's also an action-reaction pair of frictions. Dun dun dun. Yes, you get that ominous sound there. All right, so as block 2 gets pulled to the left, how is block 3 going to react to that? All right, block 3 is going to be pulled to the right because of this tension here, as block 2 is pulled to the left. So that's going to put a backward force of friction on the 2 kilogram on block number 2, and a frictional force to the left. You see, as the 10 kilogram block was pulled to the left, and the 5 kilogram block is pulled to the right, the 5 kilogram block's motion to the right is going to be resisted by that 10 kilogram block to the left. So there's that force of friction 2. You know what? Let's call that B. Instead of getting another number in this, let's say the force of friction between the blocks. Okay, force of friction between the blocks is equal and opposite on those 2 blocks. Okay, so let's add that in here. On block 2, we're going to have a right-hand force of friction from the blocks. All right. Oh, actually, I should put that up top, shouldn't I? I'm going to clean this up in a moment, folks. And for block 3, it's being pulled to the right, so the force of friction from the block is going to go to the left on that one. Okay, there it is. Am I done now? Actually, I'm not. Remember that there's a table in a block 2, also, I should say. And it's going to be resisting the left-hand motion of that 10 kilogram block. So I got the force of friction from the table we're going to add in there. Force of friction from the table. Okay, now we're actually done. This is what I mean by bloated. There's a lot of stuff going on here. And oh, I should say that let's keep consistent colors here, shall we? Block 3 is going to be going to the right. That's the positive direction of acceleration for block 3. Okay, there's its motion. Block 2 is going to the left, and block 1 is going down. All right, I think I got everything consistent here. Let's pretty this up a little bit. We've got block 2 with 98 newtons down. You know what? This is not going to get any prettier. I'm just going to move on instead of waste your time. We got 1, 2, 3, 4, 5, 6, 7 forces acting on this block 2. It's kind of caught in the middle there. 4 forces on block 3 and only 2 forces on block 1. So I'm going to start just to kind of keep everything up here as high as possible. Let's get rid of some of those. There we go. Clean that up. We're going to take the sum of the forces acting on block 1 equals mass of block 1 times acceleration. Now all these blocks, if this one moves down and accelerates down, it'll be the same as the acceleration of the 10, it'll be the same as the acceleration as the 5. They're just going to be moving in different directions. But the acceleration rate, that magnitude, is going to be the same for all of them. So I'm just going to leave it as an A. So some of the forces on 1 is just the up and down forces. We've got 196 being the positive direction. Remember, my positive over here is down, minus T1 going up. And that equals mass 1, 20 kilograms, times A. There's equation number 1. I'm going to give that a purple circle, just so we don't lose track of it. That's a rectangle. Good one. Now we're going to do, not to run out of space here, I'm going to do sum of the forces on 3, because that one's a little shorter. Okay. Now 3 has an X and a Y direction. So I'm going to go ahead and do the Y direction first. Equals mass 3 times, what's the acceleration in the Y direction going to be? Well, this block is not accelerating in the Y direction. There's going to be a 0 Y direction acceleration there. All right, so I'll just point that out first. That'll make this side easier. And the y direction, we've got normal force of the blocks, block from below pushing up, and the weight pulling down. Oh look, in the y direction we just get that the normal force FNB is equal to the weight of block 3. That's important. You need to know that, especially when we get into friction for those two blocks. And then we've got some of the forces on 3 in the x direction. Now in the x direction, it's going to accelerate with magnitude A. So I'm just going to leave that as an A. To the right, we've got T2. Remember, right is positive, so I'm going to make that do that first. T2 minus force of friction between the blocks. And that equals the mass of block 3, which is 5 kilograms, times A. All right. Now we get to a point before I leave this and have to do it later. We don't know what tension 2 is, but we're going to substitute mu of the blocks. Okay, I'm going to call this mu B. I called it mu KB before, and we're just assuming all this is kinetic friction. And I call this, oops, wrong one. That would be mu T, and this would be mu B, just to keep all the subscripts the same. So we'll call this mu B, the blocks, times FNB equals 5A. And here we can see that we're going to have a number out of this. Mu B is 0.45, and FNB is 49. Plug that in. Okay, so we have another expression. Let the equations do all the work for you. There we go. So we got T1 in terms of A, we've got T2 in terms of A, and we also have the FNB if that ever needs to come up again. All right. Are we done yet? No, we haven't done block 2, and I'm saving the best for last. Here we go. Remember, bloated, but we're still doing the same exact thing. Let's sum the forces, and let's start with the y again on block 2 equals mass of 2, and the y direction again, this block is not accelerating up or down, so the A in the y direction is going to be 0. Here we've got y direction, we've got F in the normal force of the table going up minus 98 minus F in B. Remember that block, block number 3 on top, it's pushing down with the amount of its weight. Do you see that? F in B is its weight. Doesn't that make sense? The downward force is the weight of the block on top of it. And look at what happens here. The normal force on the table is equal to the weight of the big block plus, remember this is 49 newtons, plus the weight of the top block. Should make sense, right? And that's 147 newtons. Let me circle that. Might need that. And what might be our final piece here that links everything together is, not surprisingly, the one in the middle that links everything together. So this should be our last sum of the forces of 2 in the x direction equals mass 2 times A. So it's going to accelerate to the left, hopefully. It looks like all the numbers are working out so far. So let's see, T1 goes to the left, all right, minus T2 to the right, minus friction from B, from the friction of the blocks, minus the friction from the table. Hopefully all that makes sense. T1's pulling and everything else is resisting. On the right side, we got mass of 2, which is 10 kilograms, times A, the acceleration rate. Okay, so what is all this? Well, before I just go plugging everything in, do you see how we're going to have a T1 equal to 20A minus, oh no, Other way around, other way around. If we add T1 to this side, we have to subtract 20A from that side. So this will be 196 minus 20A. There we go. Okay, that'll be the useful form there. And over here, we're going to have T2 being equal to 5A plus 45 times 49. So 0.45 times 49. $49 times 0.45. Not 245, 0.45. There we go. 22.05. I'll just call it 22. Plus 22. Okay, so that's T2. You see we have a T1 in terms of A. We got a T2 in terms of A. So those will be helpful. But before we plug those in and make a bigger mess before we clean it up, let's substitute. This is the kinetic friction, so this is mu B times normal force of the blocks minus mu T. This is the table friction minus times normal force of the table equals 10A. Be meticulous. Don't forget any piece of this here. All right, might bite you. So now we can substitute everything in that we know, and I'm going to just sub it in down here. T1 is up there at the top, 196 minus 20A. So we've got a 196 minus 20A. I'm only putting in parentheses so we can see the substitution. Minus T2. T2 is 5A plus 22. Minus mu B. Mu the blocks. Between the blocks is 0.45 and with the table 0.35. So 0.45 and FNB, I have that, 49 minus mu of the table is 0.35 and normal force of the table is right over here, 147 equals 10A. Okay, we got everything in terms of numbers and A bloated, right? All this is, it's a headache, but it's all straightforward. It's still the same thing we've been doing. Friction equals mu times normal force, substitute that in, and letting the equations do all the work. All right, so let's get all these terms out here, minus 20A. Here we got to distribute this negative, minus 5A, minus 22. Let's get a number out of that. I think I just did that one, didn't I? Is that 45 times 4? Yep, that's 22. There's another 22. Interesting. And minus, oh, look, that 22 happens twice. That is the friction of the block, right? You see there's a friction of the block resisting the top one and the bottom block. So it's going to be in there twice. There it is. Friction of the block is in there twice. I knew I did that before. All right, 0.35 times 147. So letting Newton's second law teach you about what's going on, it's valuable. So this is 41.45. I'll just call it, I'm sorry, 51.45. I'll call it 51.5. Okay, so that's this piece there. That equals 10A. Let's bring all the A's to one side. So this is negative 25A. We're going to add 25A to both sides. And then take care of all the rest of this stuff. So it's 196 minus 22 minus 22 minus 51.5. Hopefully, good, that's a positive number. And we get 100.5 equals 35A. It's cleaning up. It's cleaning up. 100.5 divided by 35. 2.87. You get to the end and you're like, oh, that's not exciting. We're at the end. We did all that work and it's just like a little number. It's kind of like a letdown at the end of a really long video game. Been working, and it just, you know, you beat the boss and it just ends. It makes you want to go back and keep playing. And it's like, I want to keep playing. I don't care about beating the game. I just like playing, right? So that's what all this is. Like, get down to, oh, you know, what's the point in calculating it out? We did all the hard part. You know, do we really need to do this? But it's good to come up with that final answer there. 2.87 meters per second squared. This is a number that you're going to remember in 50 years. Not really. But anyway, I just wanted to show you that even though you might have a complicated system, the work isn't complicated. It might be bloated, but not complicated. And I hope this is helpful to you in your studies of friction. Thank you very much.